Welcome to the last part of our Unit 11 lecture series. We're going to talk about the ocean floor. Champ and I are back again, ready to teach you all about oceans. Most of the ocean life lives near the top, about 90% of it. Nuclear submarines, about 800 feet down. Deepest scuba dive, a little over 1,000. Sunlight starts to disappear around 3,300 feet. Deepest whales go about 8,200 feet, as you can see here. Titanic, about 12,500 feet. Oh, deepest living fish, 25,000 feet down. Alright, we're already deeper than Mount Everest at 29,000 feet. And the Challenger went all the way to 36,070 feet. So a reference point to think about when we just saw that video is each story of a building is about 10 feet tall. So the deepest that Challenger submarine went was 36,000 feet down. So that's about 3,600 flights of stairs you would have to walk down to get to that. That's a long way. So how did we get to the point where we went all the way down to what we think is the deepest part of the ocean? So to know how we got there, you need to look at how we used to study the ocean floor. So the ocean floor is, in some parts it has thermal vents. They could be very, very hot. They produce liquid sulfur and carbon dioxide gas bubbles. There are organisms that live near these vents, especially types of bacteria, and they thrive off of those types of things that are given off. There is no natural light on the ocean floor. Some animals produce bioluminescent lights, but there's no natural sunlight down there. The temperatures are a few degrees above freezing. It's very, very cold, but not so cold that the water on the bottom of the ocean is frozen. And the water pressure is 1,000 times greater at the bottom on the ocean floor than it is at the sea level, which is why scuba divers have to wear gear when they go down. They have to slowly go down and slowly come back up so that the pressure doesn't crush them from the inside. There's also the submarines and other things they use. They have to be equipped to withhold the pressure without being crushed like a soda can when they go down underwater. So it took a long time to kind of figure out how to design something with the technology we have that could go down to those depths because of the pressure changes. Move myself over. I can't. Okay, cool. Despite the crushing pressure changes, there is still life that lives at the bottom of the ocean. If we were in school, I'd be showing you a lot of Planet Earth videos about this, and they're really cool. So if we're able to go back, you will definitely get a chance to watch those. More about the study of the ocean floor. The Mariana Trench was first discovered in 1875, so that was a pretty good while ago when it comes to New Age technology. And it was discovered by the HMS Challenger. It used equipment on the Challenger to create a map of the ocean floor for the world under the seas as we know it. And this includes instruments for taking samples, sounds, and temperatures under the ocean floor. All right, so more about studying it, because we don't understand how we know what we know if we don't look back on how we studied it. So during World War I, which is about 1914 to 1918, different countries needed to be able to detect submarines that were in their area, so they came up with a thing called sonar, and this was started being seen more in 1915. Sonar stands for Sound Navigation and Ranging. It uses sound waves to figure out how the ocean floor looked, and it was able to show off mountain ranges and trenches. And if there was a submarine in the way, then the sound waves would have come back and reflected off of that and shown that accordingly. In the picture over here to the left, you can see the lighter warm color schemes up here at the top are the mountain ranges underneath the water, and the deeper and darker the blue is, it represents trenches. Here's another picture of a boat using sonar imaging to map out the ocean floor. Right, studying the ocean floor, scientists now use satellites. They still use sonars on boats for some things, but they do take the newer technology into effect to help them out. So scientists now use satellites to explore the oceans. It's way more effective. You can cover more areas and even dangerous areas that maybe you couldn't get to on a boat before to help you study the ocean floor. You have a geosat or geosatellite, which is a satellite that was once a really top secret military satellite, and now they use it to help study the ocean floor. Not so secret anymore, especially since it's on our notes here at Westside. These geosatellites show very, very high detailed maps on the bottom of the ocean. So back before it was just using boats and sonar, but now we're upgrading up to these satellites to help us. And they can also not only show the ocean floor map, but they can also help us see and study surface movements and currents, tides and waves. So it really helps with monitoring sea levels, can help us with hurricane detection. There's a whole bunch of new things that satellites can provide for us that regular sonar back in the early 1900s couldn't provide for us. But started off small, worked our way up to satellite. All right, so now to the fun stuff, the ocean floor. So we're really going to talk about different parts of the ocean floor, how to recognize it and identify it, and how to label it. So there are two major regions of the ocean floor. You have your continental crust and you have your oceanic crust. Continental crust is made of granite. Continental crust is what you're standing on now. Continental, this is the land part. This part also extends out a little bit into the water right off the beaches, but continent crust made of granite, oceanic crust, which is underneath the water in the deep ocean depths. This is made of basalt or basalt, however you want to pronounce it. You do you. This is cooled lava. So new floors being formed on the bottom, lava coming up from the bottom, those thermal vents, kind of regions like that. We're going to talk about mid-ocean ridges and stuff later on. I'll explain it more. But basalt, cooled lava, oceanic crust. Continental crust, what you're standing on, granite. All right, so there's a difference between those two. You can see in the diagram here. All right, so this is a very important diagram. You will see it over and over again on this PowerPoint slide. These are things that you'll need to know and need to know how to identify. So let's see, we'll use yellow. Continental shelf. Here, part of the continent, part of the continental crust. Just like a shelf you can set things on. So this is kind of where we would go out on the beach, on the continental shelf. Very gradual slope down. Is near the surface of the water, and most life lives here. All right, you have the continental slope. It's where it's starting to slope down. All right, still a part of the continental crust. Then you have the continental rise, which is where it's changing from continental crust to oceanic crust. So it's starting to rise up, not quite a slope like a slide, but just rising up. And you have your oceanic crust here at the bottom, and this is a part of the what is called the abyssal plain. It's like the abyss of the bottom of the sea. So the abyssal plain, plains like the Great Plains, part of the oceanic crust at the bottom of the ocean, and then everything else that says continental is a part of the continental crust. Okay, so continental shelf is what we're going to talk about first. On the um, continental crust were once above water, but since has been covered with water. So either tectonic plate movements have caused it to move underwater, or global warming and the glaciers melting has caused it to move underwater. But at one point, this might have been above water and has now been covered with water. That's why it's more of a shelf, and it still has that flat characteristic. Whereas areas that have been completely submerged this whole time have more of that slope and that rise structure on it. And you can see those here in the diagram. So here's that shelf. We're talking about this part right here in this picture. The shelf has a gentle slope, so slightly gentle slope, not completely flat, but not a steep slope like a slide. And this is underwater, and the continental shelf accommodates for 28% of the ocean floor, so about 30% of the ocean floor that we talked about is a continental shelf, and that's the part that's barely underwater compared to the rest of the ocean. Most ocean plants and animals live near the shelf. Most of them live near the shelf. Alright, just because it's at the top, it's a little flatter, a little easier surface to work on, to live on, grow reefs on. Also, it's closer to the sun, sunlight, energy, photosynthesis, producers, everything else in the food web. So this is a continental shelf. So in Chile, the land dives straight down into the ocean depths with no shelf. So that's because where Chile lands on plate tectonic, that's what we're going to talk about later. But in contrast, the Siberian shelf in the Arctic Ocean, Arctic North Pole, the continental shelf up there in the Arctic is about 1,000 miles long. But Chile has no shelf, but the Arctic one is almost 1,000 miles long. So it really just depends on where you land in the world with the tectonic plates, and also how close you are to maybe more sources of water like they are in the Arctic with the poles, and the melting waters allowed for more land that used to be not covered to be covered up. So here's an example of the plate tectonics. Waters above the nation's continental shelf belong to that nation, and shelves are used as national boundaries and quote-unquote state boundaries. So we have here a variety of different shelves being shown. So as you can see here, any land that comes around, let me pick a good color, dark blue looks good. All this land, the shelf extending off of the United States, is owned by the United States. So even though our quote-unquote country ends at certain parts along our continent, or as you would see, the landmass, we still have ownership of lands outside of that, which is where the continental shelves extend out to. So even out in the middle of the Gulf of Mexico, you're still on a continental shelf. It's not until you go way deeper out that you come off the shelf and you into the ocean deep. As you can see here out in Florida, there are some parts where the shelf doesn't go out that far. So right here, it doesn't really go out that far before you get to the really deep parts of the ocean. But like up here closer to New York, it really extends out very far. Pretty cool. All right, so now we're moving on to the continental slopes. So we're talking about the continental slope. That is here. Highlight it for you. It's part that's sloping down. It's like a slide. This is the steep sloping edge of the continent, and it goes from the edge of the shelf all the way down to the ocean floor. So this is where the drop-off is. So if you're watching Finding Nemo, they would be at the drop-off. But they're not supposed to go past. This would be equivalent to a continental slope. I call it like a slide because any materials that might be falling down from the continental shelf from erosion, the waves, the tides, etc., that stuff would slide down the slope and go down to the oceanic crust region. So that is a continental slope, really easy to remember. It's a steep sloping part, looks like a slide. Next up is the continental rise. This is a transitional zone. Continental rise, transition. It transitions from continental crust to oceanic crust. The sediments found here are terrigenous, or made from land, but the floor is made from basalt. All right, so sediments are made from the continental crust, or the land. That's the stuff that slides down the slide or the slope. The floor, however, made of basalt or the cooled lava, which is part of the oceanic crust. So there's a mixture of different rock types there because of its location in a transitional. Submarine canyon, probably not heard about as much, but important enough to point out. It looks like a slide that was dug into the continental slope. Looks like where maybe a submarine could fit in, which hence the name Submarine Canyon. This would be where submarines would hide, try to not be detected in a quote-unquote trench style area. These canyons were carved out of the continental shelf. So at one point they were a part of the continental shelf. They were once maybe a part of a river. I'm highlighting that here. So once when this section of the continental shelf was above water, it probably had moving waters from a river. And as the sea levels rose, the shelf got submerged, and then those areas were eroded more and more by waves and tides, causing what is called a submarine canyon. I kind of like to think of it the Grand Canyon. It's kind of carved out and dug out. Grand Canyon's carved out by a river, so were the submarine canyons. And eventually, when they came underwater, they were carved out by the ocean waters. This runs perpendicular to the shoreline. When we talk about trenches, they run parallel. They go with the plates. But the submarine canyon is perpendicular to the shoreline and it's carved out by water. Yeah, so that's submarine canyon. All right, little review on this. We've talked about the continental shelf. Well, shelf break is kind of self-explanatory. It's where the shelf breaks down. We've talked about the continental slope and the continental rise. So as a whole, we've talked about all the continental parts of the ocean floor. So we're going to move on to the abyssal plain and the oceanic crust. All right, so the abyssal plain in this diagram is located here in the darker blue. The abyssal plain, it's kind of like the Great Plains. It's the flat area on the ocean floor. All right, and this is covered in mud, and it's covered in mud because of the runoff that comes from the continental crust. This whole time I've been explaining how this slope in this region acts like a slide because it's taking sediments down and it covers the abyssal plain in quote-unquote mud. The abyssal plain is the true ocean floor, as they would call it. The continental shelf, like when you go to the beach, you're not technically on the ocean floor, you're still on the continent. And it's not until you go past the drop-off or the slope where you actually become a part of the true ocean floor. Got a little lonely, went and found Champ. All right, so Champ is here to help me talk to you about plate tectonics. This is nothing new. You learned about this when you were younger. These are the moving parts of the moving parts of the crust of the Earth. So it's part of the continental and oceanic crust, and they're constantly shifting and moving all across the Earth's mantle. The mantle, this lava underneath the Earth, is always moving because it's more like quote-unquote liquid. It's not solid, and so since it's always flowing and moving, it's always causing these Earth's crust at the top to move around as well, but very, very, very slowly. All right, so plate movements cause earthquakes, volcanoes, mountain building, ocean ridges, and trenches. Here in the Gulf of Mexico, we don't really have to worry about earthquakes, volcanoes, stuff like that, because we're not on a ridge line. But here in California, they are, and these are two sliding ridges. So they're going against each other, and that causes a lot of earthquakes happening there. Maybe some areas in the Caribbean might have to worry about that because it looks like there's several plates there. We have areas over here in Japan, in the Philippines. So over here you can see this is why they have a lot of earthquakes there. And then there's all plates all around the world. You can come back and look at this later. And depending on the way they're moving depends on how often the earthquakes and stuff might occur. But this does help with the building and creation of ocean ridges and trenches. We're going to talk about that. So the first thing we're going to talk about here is a trench. The trench is associated or caused by convergent plate boundaries. This is when one plate, the oceanic crust, is being forced under the continental crust, causing this trench that is parallel to the shoreline. This causes a deep crack where the ocean floor meets the continental crust. So it's the plate tectonics, and this is where the deepest parts of the earth are located. So these are trenches. All right, with the Mariana Trench we talked about along two plates, tectonic plates, and they cause deep cracks, like I said, in the plates. All right, so now we're going to talk about our mid-ocean ridges, so ridge lines. Here's a map that shows where the mid-ocean ridges occur. You can see one that goes right down the middle of the Atlantic. There is a tectonic plate line here. You have a ridge line here that occurs along the near California. There's a plate there. And these are caused by divergent plate boundaries. So by divergent plate boundaries, I'm going to have a picture that pops up here soon to explain those. These, the ridges are long underwater mountain chains. So the ridge of a mountain, all right, so mid-ocean ridges, mountain chains that are underwater. New seafloor is being formed here, whereas the divergent ones is being covered up. So, the convergent, the one from the trenches. The trenches one, convergent, it dives underneath the water and you're getting ocean floor being taken away. On this one, it's causing new ocean floor. So in this picture here, you can see that plate 1's going one direction, plate 2 is going another direction, causing magma to come up from underneath. And this causes new floor to be formed, and this helps create mountain chains underwater. So mid-ocean ridges. All right, the Rift Valley is the deepest valley at the center of the ridge. So the Rift Valley is inside the mid-ocean ridges. All right, it is the deep valley that's in between it. This is where the magma exactly is coming out from, and it comes out and it cools off, and then over time, as it cools, new magma comes up, it cools off, and it keeps pushing out the ridges, causing them to go upward and outward, allowing for that mountain range to occur. So Rift Valley, it's a valley between the mid-ocean range. Seamount is an underwater mountain. Mountain, mount, sea, underwater, seamount. This is caused by submarine volcanoes or volcanoes underneath the water. You might see sometimes where a chain of islands was created by seamounts and eventually turned into volcanic islands, and eventually they just turned into islands. They build up over time underwater, and like I said, when they reach sea level, they turn into a volcanic island. It is believed that the Hawaiian Islands were built similarly to these seamounts. They started as underwater volcanoes and they worked their way up over time. So this map represents the global distribution of seamounts. The seamounts occur near rift valleys, and so you can see here there's a lot that line up with the tectonic plates. There are a whole lot over here by Japan, over here on the right hand side. This is also where the Mariana Trench occurs. And so there's seamounts all over the world. The closer you get to the poles, there's not as many, but there are still some. As you can see here in the Gulf of Mexico, we really don't have that many. And then there's only some kind of in the south near the Caribbean. All right, next we have is an atoll. This is going to briefly describe how an atoll is formed. So first, a seamount above water is an island. So it starts off as an island. It's above the water, number one. Coral reefs start to form around the island. So here we have coral reefs forming. So it's part two. All right, over time, wind and wave erode it and level out the seamount. All right, so wind, waves, level it out. You still have some of the coral reefs here. And then those same pictures underneath correspond with that. So this is when the island eventually goes back underwater, but it still has a coral reef around it. As you can see here in part 3, there's still that coral reef around it, even though it's not, the seamount itself is no longer above water, and that's what makes it to be called an atoll. It used to be atoll, and now it is not tall. Atoll, not tall anymore. Used to be a tall tell, but now it's just an area that there is maybe a seamount underneath that's no longer above the water, but once again the coral reef is still attached. So it is still bringing life and allowing things to live there, even though it's no longer above water. Next up, we have a guyot. This is a flat top seamount. All right, so you used to have a seamount, waves, wind, cut it down until it was underwater, and it is flat topped. All right, the difference between an atoll and a guyot is a guyot has no coral reef. It is just a flat topped, used to be volcanic mountain island, and it eventually got worn down and tore down until there was no more life living there. It's a flat top surface underneath the water. No coral reef with the guyot. Yes, coral reef with the atoll. All right, Champ, and I hope you enjoyed learning about the ocean floor and all the features that go with it, all the way from the continental shelf down to the trenches, where all the life lives, to where there's no sunlight. So don't forget to review the vocabulary terms. There's a lot of terms on this. Understand how to label the diagram. I put one on Google Classroom for you. I hope you enjoyed your last note part of Unit 11 before your Unit 11 test, and hopefully we'll be back to school soon. Say bye, Champ.